Okay, hello everyone. Welcome to Calc 3 for the summer 2021 semester. And we'll be covering a lot of topics in a short amount of time. So I'll try to be as thorough as possible while still keeping up a pace that will allow us to get through everything that Calc 3 that we should cover in Calc 3 in those 8 weeks. And so to do that, I'm going to split lectures into parts so the videos aren't so long here. Because to cover that much material in that short of amount of time, videos are going to have to get pretty long. And I don't want super lengthy videos, so we're going to break lectures into parts here to make the videos a little more manageable. And so for the first lecture here, let's just start off by talking about parametric equations, okay? And so what are parametric equations? Well, let's just consider a continuous function here, okay? Take a continuous function. Say y equals f of x. And we know that we can observe a continuous function geometrically as a graph or a curve on a plane in two-dimensional space. And let's say this is a continuous function over some interval, say maybe on a to b. Okay, and so here could be a, here could be b, two real numbers on the x-axis, and then we have some continuous function. Maybe it looks like this over this interval. And we have more than one way of describing what's happening here, and we can use different methods that benefit a given scenario or application a little better, right? So normally what we do is we look at a curve and we describe where you're at on the curve by 2 points, or by two numbers, x and y. And this gives you a point on the curve, and as you vary, you describe different points. And what we can introduce now is a parameter. So let's introduce a parameter. The parameter is going to be an independent variable. So we'll call this parameter t. Intuitively, it's helpful to think about it as time sometimes. So let's introduce the parameter t. And if we introduce a parameter, well, then we can write these x coordinates and these y coordinates as functions of this parameter t. So we get something that looks like this. We get two functions, x equals x of t and y equals y of t. Okay, and these are what we call the parametric equations. Okay, and these are interval for t, right? We had an interval for x, like where this function was continuous over. We also have an interval for our parameter t, and this could be between, say, 2 times, say, t1 and t2. We'll take a look at an example and see where these parameter bounds come into play. And before we take a look at an example, let's quickly see about what is going on intuitively here. Intuitively, what the parameterization of a function, these two functions, these parametric equations here, what it's doing is intuitively you can think about this as, so now I'm no longer indicating where I'm at on a curve based on like its spatial position on the graph. Now I'm kind of thinking about this curve and points along this curve as, say there's a particle traveling along this curve. And how a good way to think about what parametric equations are doing is it's telling you after this much time has passed, you've moved to this point on the curve. So, you know, we're starting at t1. Say this is time t1, and this point would be, if you'd like to think of it again in rectangular coordinates, this would be the point x of t, y of t, t1, excuse me, y of t1. This would say, when you start observing this particle, this is where it's starting on the curve. And as time progresses, the particle moves along the curve, and it ends up over here at time t2, which again, you could indicate in rectangular coordinates or xy coordinates as x of t2, y of t2. And so these basically say at what time t, or at a given time t, my particle along this curve is at this point. And both parametric and the rectangular coordinates describe the same curve. It's just intuitively there's kind of a different and maybe a more advantageous way of thinking about them. So now that we know what parametric equations are, let's do an example. Let's do an example. I want the dark blue. There we go. Let's do an example. So let's sketch the curve. So let's find the curve given by the following parametric equations. We go x equals t minus 1, and y equals, again, for the sake of shortening notation a little bit, I will sometimes drop like the x of t and just write x, and drop the y of t and just write y. But we know kind of behind the scenes, this is like x of t, and this would be y of t, right? So here we have 2t plus 4. And we want to look at this curve on the interval t between -3 and 2. Okay, and if you just want to find a curve when you have relatively easy numbers and bounds, I would just plot points here. So let's plot points. And this helps us get an idea of how parametric equations behave. So here we'll have our xy axis, or x and y axes. Okay, and we're going to start, I mean, we can choose like a handful of points to pick. Let's just start with the lowest bound. Let's start with t equals -3 and see what we get here. Well, if we plug in t equals -3, we would get that x equals -4 and y equals, it would be -6 plus 4, so -2. So we know our first point on this curve is at -4, -2. So we'll say down here, this is the point where t equals -3. Okay, and so let's look at the next point here. You know, we could just pick some values to be relatively convenient for computation. So when we have t, we can just pick integers, say. So when t is -2, x is going to be -2 minus 1, which is -3. And y is going to be, plug in -2, so -3 is 0, right? So there's something here. This is t equals -2. And I won't do all of them, but let's do a few more. So t equals negative. When t is -1, we get -1 minus 1, which x is -2 then. and then y would be -2 plus 4, so it should be 2. And so we get the point -2, 2. So here this is t equals -1. And maybe you can get the idea here for the rest of them. I'll do the very last one. If you kept going by the integers and we went up to our upper bound here to 2, right? If t was 2, we would get x is 1, y is then 8. So we'd go, say, wherever 1's at, and then say maybe 8 is up here, right? We get some point. And then you can see kind of the general trend that these lines, or these points make, and we get a line, right? It's not a very good looking line here that I've drawn, but it is indeed a line. And you can see here both t minus 1 and 2t plus 4 are linear functions. So it makes sense that we would get a line out of this parameterization. Okay. And so that's kind of an idea of how parametric equations are behaving. You know, we say at time t equals -3, this particle lives here along the line. But as 1 second progresses at time t equals -2, the particle is now moved to this spot, and et cetera, et cetera. And you kind of plot all those points, and then you get this line here. So next, we want to talk about going back and forth between just like rectangular coordinates, say some function in y of x, and parametric equations here. They wouldn't be very useful to study if we couldn't easily get back and forth between both. So now let's look at how we can take something that's parametric and get back, kind of recover what the original function is in terms of x and y coordinates.